Today's presentation relates to Chapter 1 of Sommerville's Software Engineering 10th Edition text. This presentation provides a synopsis of the material covered in this chapter, along with some discussion questions. I'm going to conduct a lecture on the premise that you've read the chapter, although I know that may not be true. Let's start with some warm-up questions. Question 1. What is software engineering? What makes it different from other engineering endeavors? I'll give you a few moments to ponder this before we get to one of our formal definitions. Sommerville's definition is an engineering discipline that is concerned with all aspects of software production, from the early stages of system specification to maintaining the system after it has gone into use. What do you think of this definition? Is there any way that you would redefine it? Question 2. Given the stakes involved in software engineering, do you think professional software engineers should be certified in the same way as doctors or lawyers? Question 3. Fred Brooks argues that some of the best software has been produced by two programmers working in a garage. Why is all software not produced that way? In general, I think it's a matter of scale. Two programmers can undertake a fairly simple game and be successful at producing it. After all, Jobs and Wozniak were quite successful at producing Breakout. However, larger modern efforts such as the latest release of the Elder Scrolls requires a large team of programmers, artists, writers, testers, management, etc. In order to answer the question of what is software engineering, it's probably necessary to define software. Software products are computer programs and associated documentation such as requirements, design models, and user manuals. Software products can be generic, developed to be sold to a wide range of different customers, for example, PC software such as Excel, or bespoke, developed for a single customer according to their specification. New software can be created by developing new programs or reusing existing software. So, back to software engineering. There are two key aspects of the definition that you see here. One is an engineering discipline, and here we need theories and methods, but we also need to get things to work at the end of the day. The second bullet point treats this aspect in more detail and says all aspects of software development. Not just concerned with the technical aspects, you need soft skills such as project management and people skills. As a result of this definition, software engineers should adopt a systemic and organized approach to their work. Software engineers need to use appropriate tools and techniques depending on the problem to be solved, development constraints, and the resources they have available. The term software engineering was first proposed in 1968 at a conference to discuss the software crisis. In particular, this was a NATO-sponsored conference on software engineering that took place in Garmisch, Germany. What are the differences between software engineering and computer science? Well, computer science is concerned with theory and fundamentals such as algorithms, whereas software engineering is concerned with particularities of developing and delivering useful software. So there is also a question as to whether software engineering belongs in the realm of CS, engineering, or business. We're going to assume that it belongs in the realm of computer science. In practice, it's a bit of all three. Systems engineering is concerned with all aspects of computer-based systems development, including hardware, software, and process engineering. Software engineering is a part of systems engineering that's concerned with developing the software, infrastructure, control, applications, and databases in the system. In general, roughly 60% of costs are development costs, 40% are testing. For custom software, evolution costs often exceed the development costs. And costs vary depending on the type of system, the requirements of the system, and the system attributes you require, for example, performance or reliability. The distribution of costs also depends on the development model that you're using. Some models put a large portion of the cost up front, for example, formal methods, while others, such as Agile or the waterfall method, put the cost at the back end. First and foremost, software should deliver the required functionality and performance to the user. It should also have maintainability, that is, it must evolve to meet changing needs. Dependability, it should be trustworthy. Efficiency, it should not make wasteful use of system resources. And acceptability, it must be accepted by the users for which it was designed. According to Sommerville, the key challenges in software engineering are heterogeneity, delivery, and trust. Heterogeneity is developing techniques for building software that can cope with heterogeneous platforms and execution environments. Delivery is developing techniques that lead to faster delivery of software, and trust is developing techniques that can demonstrate the software can be trusted by its users. What is the best technique? Well, the best technique is the one that is appropriate for the job at hand. For example, if you're building an automatic navigation software for light rail, you'll probably want formal methods. Video games are best suited to iterative prototypes, and self-contained in-house tools might be best approached using an agile development methodology. There are 4 fundamental activities in software engineering: software specification, software development, software validation, and software evolution. This looks very much like the 4 steps you might have learned from CS150 or CS151. Here there is an additional step of software evolution, which repeats the first 3 steps until the software is ultimately decommissioned. There are 4 case studies that appear throughout the book: an embedded system and an insulin pump that's used by diabetics to maintain blood glucose level, a mental health care patient management system called MintCare, used to maintain records of people receiving care for mental health problems, a wilderness weather station that collects data about weather conditions in remote areas, and iLearn, a digital learning environment. One of the readings associated with the class is an article by Tom DeMarco called Software Engineering, an Idea Whose Time Has Come and Gone. At only 2 pages, it's definitely not a weighty scientific article, and it's worth a few minutes of your time. Here are some brief insights. First of all, the article is a reflection on the author's book, Controlling Software Projects, Management, Measurement, and Estimation from 1982. The key phrase in this book was, "You can't control what you can't measure." The reflective question in the 2009 paper is control the most important aspect of software development? DeMarco's conclusion upon reflection was consistency and predictability are still desirable, but they haven't ever been the most important thing. The more important goal is transformation, creating software that changes the world or transforms a company or how it does business. We've been rather successful at transformation while operating outside our control envelope. One of DeMarco's interesting points is that projects that deliver marginal value are more in need of control than projects that deliver high value. He wonders why we focus on marginal value projects. My surmise is that not every project has the capacity to deliver great gains on value, but some projects with low marginal value are completely necessary due to regulation, compliance, etc. Thanks so much for watching.